So, let's go. Right now, multiple comets are heading toward Earth. Some you can see with binoculars, some just left. One came from another star system entirely, and the scariest one, we haven't found it yet. Number 1, the visitor roster. In the last 18 months, Earth has had more notable comet close calls than in the previous decade combined. Not metaphorically, literally. 4 comets, 4 completely different stories, all of them real, all of them recent, and all of them close enough that people photograph them with backyard telescopes. This isn't a once-in-a-generation event being dressed up for clicks. This is genuinely one of the most comet-dense windows in recent memory, and scientists are still figuring out why. So, let's go through them. Because each one is different, and each one tells you something the others don't. First, January 2025. NASA astronaut Don Pettit is orbiting Earth on the International Space Station, 261 miles above Kazakhstan, and he points a camera out the window. What he captures is a comet hanging above the curve of the atmosphere, glowing against the black, looking close enough that you'd swear you could reach out and grab it. It's called C/2024 G3, but most people called it the Great Comet of 2025. In reality, it was 87 million miles away. The photograph became one of the most shared space images of the year. That's how bright it was. That's how clear. A comet so vivid it looked fake, captured by a man floating in a metal tube 200 miles up, and it was still 87 million miles away. Second, C/2025 K1, 5 miles wide. It made its closest pass to the sun in early October 2025, closer than Mercury gets, close enough that by all rights it should have been vaporized. And it wasn't. It survived. For about 5 weeks, and then Hubble Space Telescope turned toward it and watched it come apart in real time. We will spend a full section on this one because it deserves it. Third, C/2024 E1, named after the Polish astronomer Kacper Wiertzkosz, who discovered it back in March 2024. It's city-sized, it glows green, and it made its closest approach to Earth on February 17th, 2026. Here's the thing about Comet Wiertzkosz that makes it genuinely strange. It is leaving and it is never coming back. Not in 1,000 years, not in 1,000,000. Its outbound trajectory is hyperbolic. The sun's gravity isn't strong enough to pull it back. It came in from the deep edge of the solar system, swung around the sun for the first time in its existence, passed us, and is now on a permanent exit trajectory. We got one look. That's all anyone will ever get. Fourth, C/2025 R3, also known as Pan-STARRS, which reach naked eye brightness in late April 2026, magnitude 1.5, comparable to the brightest stars in the constellation Cassiopeia. Visible before sunrise from dark sites across the northern hemisphere, it's also possibly hyperbolic, also possibly a one-time visitor. There's a pattern here, and we'll get to it. And then there's a fifth. Not from the Oort Cloud, not from the Kuiper Belt, not from this solar system at all, the fastest object ever recorded passing through our neighborhood. But that one gets its own section, because it needs one. Number 2, what you're actually looking at. Before this gets stranger, you need to know what a comet actually is. Not the textbook version, the real version. Because the real version is weirder, and once you know it, every image of a comet you've ever seen looks different. Start with the color, because the color is a lie that turns out to be true in a more interesting way than expected. Comets glow green. You've seen the photos. That hazy green shimmer around the head of the comet, the nucleus buried inside it like a coal dark seed in a glowing fog. The green comes from a molecule called dicarbon, 2 carbon atoms fused together. That's it. That's the whole structure. And the reason it matters is that dicarbon is almost impossibly fragile. It can only exist in places with almost no oxygen, deep space, the surfaces of stars, the comas of comets. You do not encounter dicarbon on Earth, it would be destroyed instantly. When sunlight hits it in a comet's coma, it fluoresces. Bright green, eerie and vivid and completely natural. But here's the part that took 90 years to confirm. The same sunlight that makes the dicarbon glow also kills it. Ultraviolet radiation breaks the molecule apart before it can drift very far from the nucleus, so the green stays close. It never reaches the tail. It gets brighter and tighter as the comet gets closer to the sun, shrinking into an increasingly vivid halo. And then it's gone. The theory was first proposed in the 1930s and wasn't confirmed in a laboratory until 2021, when a team spent 9 months trying to align 3 invisible UV lasers in a vacuum chamber, nearly gave up, and then finally watched dicarbon photodissociate in real time for the first time in human history. 90 years of wondering, solved with lasers and patience. So what you're seeing when a comet looks green is a molecule that can't exist on Earth, fluorescing in the vacuum of space, being simultaneously created and destroyed by the same sunlight that makes it visible. The tail is a different color entirely. Usually 2 of them, actually. The ion tail is blue, made of ionized gas pushed directly away from the sun by the solar wind, always pointing away from the sun regardless of which direction the comet is traveling. If a comet is moving away from the sun, its ion tail is pointing ahead of it. It's always fleeing, even if the comet is chasing. The dust tail is wider, white or yellowish, curving gently along the orbital path like a scar left behind in space. Both tails can stretch 100 million kilometers. That is 2/3 of the distance from Earth to the sun. You're looking at a structure the size of the inner solar system, generated by something you could walk across in a few days. The nucleus at the center, the actual solid body, is usually a few kilometers wide. Potato-shaped, rotating slowly, and darker than coal. The albedo, which is the measurement of how much light a surface reflects, is somewhere between 0.03 and 0.06. Coal is about 0.04. The surface of a comet nucleus is one of the darkest naturally occurring substances in the solar system, covered in a thick crust of organic material that has been baked by cosmic radiation over billions of years. We used to call comets dirty snowballs. The better term, and astronomers have genuinely started preferring this, is snowy dirt balls. The ice is almost secondary. The rock and dust and dark organic crust is the majority of what's there. When that crust heats up as the comet approaches the sun, the ice underneath sublimes, skips liquid entirely, and goes straight from solid to gas. Jets of vapor burst through the surface in specific weak spots, spinning the nucleus, pushing it slightly off course in ways that have to be carefully calculated. The coma inflates from nothing to hundreds of thousands of kilometers across in a matter of weeks. A dead, dark rock becomes something alive and luminous and trailing fire. And here's the thing about where comets come from. That reframes the whole experience of looking at one. The long-period comets, the ones with orbital periods longer than 200 years, come from the Oort Cloud. A vast spherical shell of icy debris surrounding the solar system at distances between 2,000 and 100,000 astronomical units from the sun, so distant that the sun barely holds them. A slight nudge from a passing star or the gravitational tide of the Milky Way itself, and one of them starts falling inward. Slowly at first, accelerating over centuries, over millions of years. The Oort Cloud comet currently making its way toward us, the one that will be visible in your sky sometime in the coming years. It started this journey before our species existed. Not before recorded history. Before Homo sapiens. Before Homo heidelbergensis, our ancestor from 200,000 years ago. An Oort Cloud comet falling toward the inner solar system today may have started its inward journey 1,000,000 years ago, in darkness, in silence, falling toward a sun it has never felt before. Number 3, the comet that broke on camera. C/2025 K1 had already done the hardest thing. It had passed perihelion, its closest point to the sun, at 0.33 astronomical units. That is inside Mercury's orbit. Mercury itself only gets as close as 0.31 AU, and Mercury is a planet made of rock that has been baked for 4.5 billion years. K1 is an Oort Cloud comet, a first-timer, something that had never felt significant solar heat in its entire existence. It flew through the most intense radiation in the inner solar system and came out the other side intact. 5 weeks later, it didn't exist anymore. On November 8, 2025, the Hubble Space Telescope took a 20-second exposure of K1. There were 4 objects in the image where there should have been one. On November 9th, same thing. November 10th, Same thing, except one of the fragments had broken apart again. Hubble was watching a comet die in 3 installments. Here's the part that shouldn't be glossed over. Hubble was not supposed to be watching this comet. A research team at Auburn University had won observation time to study a completely different target. But a technical issue made that original target impossible to observe, and the team needed a replacement fast. They picked K1. They pointed the telescope. And right at that moment, across 400 million kilometers of space, a 5-mile wide comet was quietly coming apart at the seams. The scientist who first looked at the data, a researcher named John Noonan, described the moment he realized what he was seeing. He had expected one comet, he was looking at 4. He said they knew immediately it was something really, really special. They reconstructed the fragmentation timeline by working backwards from the positions and velocities of each piece. The comet had started breaking apart 8 days before Hubble ever looked at it. The cracks were already spreading when the telescope powered up. They caught it not at the beginning, but close enough to the beginning that they could trace the whole sequence. First time Hubble has ever caught a comet fragmenting this early in the process, and then it gets weirder. One of the subfragments, a piece of a piece, broke apart again while the images were being taken. They watched a comet become 4 comets, and one of those 4 comets become 2. In 3 days, in 3 20-second exposures. We don't fully understand why this happens. Long-period comets fragment far more often than short-period ones, and nobody has a definitive explanation for why. The best theory is that it's about freshness. Short-period comets, the ones that loop around the sun every few years, have had their volatile ices depleted by repeated solar passes. There's not much left inside to erupt. Long-period comets, first-timers, still have all their original volatile material intact. Ices that have been frozen for billions of years suddenly hitting intense solar heat for the very first time. Gas is expanding faster than the structure can handle. The nucleus doesn't just melt, it explodes from the inside out, 5 miles wide, reduced to fragments in 8 days. And here's the thing that should stick with you. A comet aimed at Earth isn't necessarily one problem, it's potentially 5. If K1 had been on an impact trajectory, we would not have had one incoming object to deal with, we would have had a fragmented cluster, each piece on a slightly different path, each carrying its own destructive energy. The fragmentation doesn't reduce the threat, it distributes it. Number 4. The alien time capsule. On July 1st, 2025, a telescope in Chile caught a faint dot moving across the sky at a speed that made no sense. Not fast in a way that's hard to notice, fast in a way that was immediately, obviously, numerically impossible for anything that belonged here. Within 24 hours, astronomers around the world had confirmed what they were looking at. The object being logged as 3I/Atlas was not from our solar system. It is only the 3rd interstellar object ever detected passing through our neighborhood. The first was Oumuamua in 2017, the one that still doesn't make complete sense, the one with the mysterious acceleration that no one has fully explained. The second was Borisov in 2019, clearly a comet, better behaved, less unsettling. And now this, 3I/Atlas, the 3rd visitor from outside. It came in from the direction of Sagittarius at the galactic center on a retrograde orbit. Retrograde means backwards. It was traveling in almost exactly the opposite direction of every planet in the solar system. All 8 planets orbit the sun counterclockwise if you look down from the north. 3I/Atlas was going clockwise, alone, moving against the current of everything in the solar system with complete indifference. Its eccentricity was 6.14. To put that in context, Earth's orbit has an eccentricity of 0.017, which is nearly circular. An eccentricity of 1 means the object is on the precise boundary, moving exactly fast enough to escape the sun's gravity, but not faster. An eccentricity above 1 means the sun can't hold it. An eccentricity of 6.14 means the sun's gravity wasn't even close to being a factor. 3I/Atlas was never here. It was always just passing through. When it was first detected within the orbit of Jupiter, it was traveling at 137,000 miles per hour. Pulled inward by the sun's gravity, it accelerated. By perihelion, it had reached 153,000 miles per hour, the fastest solar system visitor ever recorded. To give you a sense of what that means, at that speed, you could travel from New York to Los Angeles in about 70 seconds. You could circumnavigate the Earth in less than 3 minutes. The moment the discovery was confirmed, the scientific community mobilized in a way that was almost unprecedented. Every available telescope and spacecraft was redirected toward it because everyone understood immediately that this was a once-in-a-lifetime, possibly once-in-a-civilization, opportunity. Here is what was pointed at it in rough order. Hubble, which estimated the nucleus diameter at somewhere between 1,400 feet and 3.5 miles. James Webb Space Telescope, which captured near-infrared spectra. The Parker Solar Probe, watching it from October through early November 2025. The Mars Reconnaissance Orbiter, which photographed it from 19 million miles away with its high-resolution camera on October 2nd. The Sphere-X Observatory, which collected data for about a week. The Lucy spacecraft, which spotted it from 240 million miles away. A mission designed to study asteroids near Jupiter, accidentally witnessing something from another star. The Psyche spacecraft, 4 observations over 8 hours. Europa Clipper, currently on its way to Jupiter, not scheduled to arrive until 2030, detected oxygen and hydrogen streaming off the surface, confirming massive outgassing activity. Stereo, Punch, and at least a dozen major ground-based observatories. An interstellar visitor mobilized more scientific resources than almost any single object in the history of astronomy. Its coma, the gas cloud surrounding the nucleus, was estimated at around 700,000 kilometers across. The Sun is 1.4 million kilometers wide. The coma of 3 I/Atlas was roughly half the width of the Sun. Earth is 12,700 kilometers wide. The coma was 55 times wider than our entire planet. It came closest to Earth on December 19, 2025, 168 million miles. Then it was gone. It is currently racing out of the solar system and will never return. In a few thousand years, it will be in the dark between stars again. In a few million years, it will be beyond the reach of any instrument we could ever build. It will wander between galaxies for billions more years, carrying whatever it carries, going wherever it goes. Now, about the age. Scientists estimate 3 I/Atlas is between 3 and 12 billion years old. The solar system is 4.6 billion years old. If the upper estimates are right, this object formed before our sun existed, not before Earth, before the sun. The star it was born around, if that star was even remotely typical, has already lived its entire lifespan and died, become a white dwarf or collapsed, or scattered its material across space. The object that just flew through our solar system may be an orphan from a dead star, drifting through the galaxy for longer than Earth has existed, carrying frozen chemistry from a world that no longer has a sun. Its chemical composition was slightly different from our comets. The same types of molecules, water, carbon dioxide, carbon monoxide, but in different ratios. A fingerprint, specific. Traceable, in theory, to a particular kind of stellar environment, from a star that ran hotter or cooler than ours with a different dust disk, a different chemistry in the early chaotic era when solid things were first forming. We got one pass, one set of observations, and then it left. The alien spaceship theory made the rounds. A Harvard astrophysicist suggested it seriously in a paper published in July 2025. It's not a spaceship, it has a coma. Spaceships do not spontaneously grow 700,000 kilometer gas clouds from outgassing ices when they approach a star. The physical behavior of 3 I/Atlas is completely consistent with a natural comet. But the actual truth is, in certain ways, stranger than the theory. A natural object older than our solar system, born in a dead star system, that spent billions of years in the dark between stars, passed silently through our neighborhood, and left without slowing down. We didn't send it here. Nobody did. It just came. Number 5. The part nobody talks about. Here's where this changes. Everything so far has been spectacular, extraordinary. Even a comet photographed from orbit, a comet that fell apart on camera, a city-sized green intruder from the edge of the solar system, a visitor from another star older than the sun. None of it was dangerous. All of it missed. We saw them coming, we watched them pass, we pointed instruments at them, we got data. The entire experience of the last 18 months has been comforting in a way. Look what we can detect. Look how well we track these things. Look how prepared we seem. Here's the problem. We only got to do any of that because those particular comets came from directions we could see, at times we could observe, on trajectories that gave us months of lead time. And for a specific category of comet, that is not guaranteed. It is not even close to guaranteed. For near-Earth asteroids, our tracking is genuinely impressive. We've cataloged roughly 95% of the kilometer-plus rocks, the civilization-ending sized ones, in orbits that cross Earth's path. We know where most of them are. We have decades of warning for the dangerous ones. We demonstrated in September 2022 with the DART mission that we can physically redirect an asteroid by flying a spacecraft into it at high speed. The asteroid Dimorphos had its orbital period changed by 33 minutes from a single impact. We have a working planetary defense tool for asteroids. Long-period comets are a completely different category of problem, and it's one that planetary defense researchers have been quietly worried about for decades. A long-period comet doesn't follow a known repeating orbit. It doesn't come back every 76 years on a predictable schedule. It falls in once, or maybe it falls in and escapes and returns millions of years later. It can arrive from any direction, above the plane of the solar system, below it, from behind the sun, from any angle at all. And with current detection technology, we typically can't see one until it's about 5 astronomical units from the sun. That sounds like a lot of distance. It is not a lot of time. At 5 astronomical units out, a comet on a direct collision course with Earth gives you somewhere between a few months and, if you're lucky, a year of warning. Paul Chodas, who runs NASA's Center for Near-Earth Object Studies, put it plainly. 2 years of warning is really, really short unless you've prepared a lot on the ground. 2 years, that's the optimistic version. The realistic version for many trajectories is considerably shorter, and the physics of a comet impact is why this matters so much. Asteroids typically hit Earth at around 20 kilometers per second. Comets hit at 30 to 60 kilometers per second, sometimes faster because they're falling in from such enormous distances and accelerating the whole way. Kinetic energy scales with the square of velocity. Double the speed, 4 times the energy. A comet moving at 50 kilometers per second carries 6 times the kinetic energy of an asteroid the same size moving at 20, which means a comet doesn't need to be as big to be just as catastrophic. A comet smaller than the object that ended the Cretaceous could still release comparable energy, depending on its speed and composition. To make this concrete, Comet Hale-Bopp, which passed Earth famously in 1997 and was tracked by millions of people, has a nucleus roughly 60 kilometers wide. It was never on a collision course with us. But if it had been, if the orbital mechanics had worked out differently, the impact energy would have been approximately 4.4 billion megatons of TNT, 44 times the energy of the Chicxulub impactor that killed the dinosaurs 66 million years ago. Some models suggest an impact at that scale doesn't just cause a mass extinction, it may sterilize the surface of the planet entirely. Every living thing on land, gone. The oceans boiled at the surface. A decades-long impact winter in the aftermath. Hale-Bopp was never a threat, but it exists. It's real. And there are objects of similar scale in the Oort Cloud. The Oort Cloud, which is where all long-period comets come from, contains an estimated several trillion individual objects. We have never directly imaged it, not a single direct observation. Everything we know about it comes from reverse engineering the orbital paths of the comets it occasionally ejects toward the sun. We are inferring the existence of a shell of trillions of icy objects surrounding our entire solar system from the small fraction that fall out of it. The Oort Cloud is the single largest structure in our solar system, dwarfing the orbits of all 8 planets combined, and we have never seen it. Voyager 1, the most distant human-made object ever launched, traveling for over 40 years since leaving Earth, will take approximately 300 more years to reach even the inner edge of the Oort Cloud. We are not going there anytime soon. Now, a brief and honest note about where established science ends and modeling begins. What follows isn't fringe, it's mainstream scientific modeling. But it's not confirmed observation. If a star passes within approximately 10,000 astronomical units of the Sun, close enough to perturb the outer Oort Cloud, it can destabilize the orbits of billions of comets simultaneously. The result is a comet shower. an increase in long-period comets entering the inner solar system by a factor of up to 200. For about 2.5 million years. The evidence in Earth's impact cratering record suggests this has happened before, possibly multiple times. We don't know exactly when the next close stellar passage will occur. We don't have a complete enough catalog of nearby stellar trajectories through deep time to predict it. Statistical models also suggest that at any given moment there are likely several interstellar objects from outside our solar system entirely, inside Neptune's orbit right now, passing through silently. We found 3 since 2017 because our telescopes finally got good enough. The ones before 2017 simply went undetected. We don't know how many passed through the solar system in the last century. We don't know how many are passing through right now. Number 6. The mission that doesn't have a target yet. ESA has a spacecraft almost ready to launch that does not know where it is going. It's called Comet Interceptor, a joint mission between the European Space Agency and JAXA, the Japanese space agency. The plan is to launch it sometime between 2028 and 2029, fly it to a gravitational parking spot called the Sun-Earth L2 point, sitting about 1 million miles behind Earth, exactly balanced between Earth's gravity and the Sun's, and wait for up to 3 years. For a comet that has not yet been discovered. This is not a vague or preliminary concept. It has been formally adopted by ESA. The spacecraft is being built. The instruments are being developed. A mission is being assembled around a target that does not yet exist, on the theory that the target will be discovered in time to intercept it. Every comet mission in history visited comets we'd known about for years or decades. Giotto flew past Halley's Comet in 1986. We've known about Halley's for centuries. The Rosetta mission chased Comet 67P Churyumov-Gerasimenko for 10 years and orbited it for 2. Both of those comets had been around the sun dozens of times. They had been baked and stripped and altered by repeated solar exposure. The volatile material on their surfaces had been depleted over thousands of years of solar passes. What you were studying with Rosetta was a comet that had been partially processed by the sun, not a pristine one. What Comet Interceptor wants is something that has never felt sunlight before. An Oort Cloud comet on its first ever approach to the inner solar system, carrying whatever it carried when the solar system was forming before any of it was altered by heat. Or, if the opportunity arises, an interstellar object, something carrying the chemistry of a completely different star system. The spacecraft would split into 3 components on approach. One main spacecraft, 2 sub-probes, each approaching from slightly different angles simultaneously, building a 3-dimensional picture of the target from multiple vantage points at once. The first true 3-dimensional map of a pristine comet. What's in the nucleus before the sun cracks it open. What the coma looks like from all sides at the same moment. How the 2 tails connect back to the surface. 3I/Atlas proved the basic premise is achievable. Once the interstellar comet was detected in July 2025, it was trackable and observable for months before and after perihelion. If Comet Interceptor had already been sitting at L2 when 3I/Atlas was discovered, there would have been a real discussion about whether it could be redirected for an intercept. The mission scientists noted publicly that such an encounter would be relatively unlikely, but not impossible. The timing of the mission may also improve. The launch had been planned as a shared ride with ESA's Ariel exoplanet mission in 2029. But Ariel's development has slipped to 2031, and rather than wait 3 years in storage, Comet Interceptor is now exploring the possibility of an earlier independent launch. An earlier launch means more time parked at L2, more time waiting means a better chance of finding something worth chasing, and the detection side is also improving. The Vera C. Rubin Observatory in Chile, now beginning full science operations, is designed to survey the entire visible sky every few nights, going deeper than any previous wide-field survey. It is expected to dramatically increase the rate at which long-period comets and interstellar objects are discovered at greater distances, earlier in their approach. More warning, better characterization, more time to plan. The whole system, Comet Interceptor at L2, Rubin watching the sky, detection pipelines improving, is a bet. A bet that by the time the spacecraft is sitting and waiting, our eyes will be good enough to find something worth flying toward before it's gone. It's a reasonable bet, but it's still a bet. We've watched 4 comets pass Earth in 18 months, caught one breaking apart on camera, piece by piece, in 3 20-second photographs. Received a visitor from a star that may not exist anymore, moving backwards through our solar system at 153,000 miles per hour, carrying frozen chemistry from a dead world. Built a spacecraft designed to wait for something we haven't discovered yet, on the theory that we'll find it in time. And somewhere out there, right now, beyond Neptune, in the dark, falling toward the sun at a speed that would cross a continent in a minute, there's one we haven't found yet. We don't know its size, we don't know its origin, we don't know exactly when it started falling. We don't know its name because it doesn't have one yet. It just keeps falling.